good day, good night, sorry, and welcome to my part 2 on the integrated science crash course for CSEC. All right, so this is part 2. Make sure and ensure that you watch part 1 before you watch this video, because all the videos will be slowly linked together. All right, so in the last video, let's jump straight into it. We had discussed rusting, and when we were talking about rusting, a lot of other topics came up under rusting, and of course, we had to answer those questions. The same thing is going to happen with today's question. We talked about rusting in the last video, but we didn't actually talk about how to stop rusting. When we begin to answer this question, it's going to open a whole new can of worms for us. Okay? So you're in for a ride, guys. In the last video, we had mentioned that rusting needs 2 things to happen. Well, obviously you need the iron or the metal itself that is to be rusted, but you need oxygen and you need water, right? You need oxygen and you need the water. Not one of them, both of them at the same time. So, to protect a piece of metal from rusting, a good idea would be to try to keep the oxygen and water away from the piece of metal. That seems like the most logical thing to do. So, what about painting? Let's say you have a piece of metal. If you paint it, so you paint the surface. If you paint the surface, you are actually, to a point, limiting the amount of oxygen that can come in contact and limiting the amount of water that can come into contact with the metal. So painting does a pretty good job at delaying rusting. But after a while, the paint will break down. And once the paint breaks down, the water and the oxygen are free to do what? Come in contact with the metal. But this is a decent way of preventing rusting. Okay, another way is grease or oil. So instead of painting the metal, right, what you can do is coat it with grease or oil. And of course, that also forms a nice protective barrier around the piece of metal. And it prevents the oxygen and water from coming in contact with the metal. All right. So another method is something called galvanizing. It's very popular in past papers. Let's say we have a piece of iron and we want to protect it. What we can do is coat it with another metal, and that, well, next metal is zinc. So galvanizing is protecting the metal using what? Zinc, okay? And of course, the zinc, because it has a protective barrier around it, it prevents the oxygen and the water from coming in contact. Now that's one way zinc protects the iron. It prevents the oxygen and water from coming in contact. But zinc actually protects the iron another way. Let's say that the zinc breaks down and it exposes the iron, right? So water, I'm just going to put well, W for water and O for oxygen. So now the zinc has broken down. The water and oxygen can now come in contact with the iron. So you're probably saying, once the zinc layer goes, the oxygen and the water is free to attack the iron. But I'll have to explain this later on as we go along. Even when the barrier is broken, the zinc still does a good job at preventing the rusting. Believe it or not, even when the zinc is broken. It will be explained, don't worry. And another method of protecting metal is something called sacrificial protection. Let's say, right, we have iron or steel, and we want to protect the iron or steel from rusting. Okay, like a boat, like those huge steamboats or those huge ocean liners. They're made of iron, but actually made of steel. You don't want a boat on the ocean to rust out over a few years. So what they actually do, they take a more reactive metal. You're probably wondering what I mean by a more reactive metal. It will be explained just now, so don't worry. All you need to know is that you take something called a more reactive metal and connect it to the iron or steel, whichever material your boat is made of. And that will protect this. What does sacrifice mean? If you sacrifice your life for someone, that means you give up your life for them. So when it's time to rust, it's kind of like the rust has a choice. I'm going to rust this or I'm going to rust this. What happens? The more reactive metal takes the bullet for the team. In other words, the more reactive metal will rust and it will save the life of the iron or the steel. So you're probably wondering, how does that happen? How does taking a piece of wire or connecting it to the iron or steel will prevent the iron or steel from rusting? I'm just telling you it does. But I have a duty to explain that to you. Okay? So, to understand what we mean by a more reactive metal, we need to look at this chart here, which you need to learn off for your exam. Okay? All right? I'm just saying good night to someone here. Good night, Jill and Russ. Good night, good night. So this is a live, well, it was a live video. So what we need to learn off here, right, is, well, these are the metals, well, some of the metals that are found on your periodic table. Some metals are more reactive than other metals, okay? I have to explain what I mean by more reactive just now. But you need to memorize this chart in this order. Potassium, sodium, calcium, magnesium, aluminum, carbon, zinc, iron, tin, lead, hydrogen, copper, silver, and gold. Carbon and hydrogen are not metals, but they are usually included in this table for comparison. How it works, as you go upwards, the metals become more reactive. And as you go downwards, it becomes less reactive. In other words, potassium is the most reactive of everyone in this list. And gold is the least reactive. Okay? Reactive, one way of kind of like explaining what I mean by reactive, it's how willing it is to take part in a reaction. Potassium is always willing to take part in a reaction. Gold is like this lazy person and doesn't want to do anything. So if you ask him, hey, you want to take part in a reaction? He will be like, no. But as you go upwards, the metals get more and more willing to take part in a reaction. That means the metals on top are more willing to combine with other elements. Those below are not willing to combine with other elements, better known as a reaction. So you're probably wondering how to memorize this chart. There's actually an easy way. It's a little a rhyme or sentence. I don't know what's the English term for it. Notice potassium starts with P, sodium with S. So this is it. Please stop calling me a crazy zebra. Instead, try learning how copper saves gold. You see this chart here? It's called your reactivity, your metal reactivity series. Let me write that in here. This little chart here is called your metal reactivity series. And you see that little rhyme that I just said there? If you go on Google and type in metal reactivity series, way to remember it, that same rhyme that I just said there, it's all over the internet. So that's nothing I came up with. That's already been out there for years. Okay? So let's see. Different substances react with different compounds. You see, everybody above calcium reacts with water. So calcium, sodium, and potassium all react with what? Water. Anyone below this red dashed line does not react with water. So zinc and iron and whatnot do not react with water. I know what you're probably saying, but I know iron reacts with water to get what? Rust. No. Iron reacts with water and oxygen. Only when these two are present, then we get rust. But this is water alone we are talking about. Okay? Steam. So when you boil water, you get steam. You see everybody above this pink dash line, it reacts with steam. So iron, zinc, carbon, aluminum, magnesium, and calcium, sodium, and potassium. Everybody above that line reacts with steam. So in other words, sodium reacts with water, but it also reacts with what? Steam. And it's similar things for acid here. Everybody what? Above the lead line, above the dashed line here, everybody above that line reacts with acids. And everybody above the green dashed line reacts with oxygen. You need to memorize this. All I could really do is show you the chart, and it's up to you to memorize it. I did come up with a way to help students remember. I don't know if you want to hear it. My opinion, I kind of leave, but I'll still tell you. Let's pretend we have a glass of water. When you drink the water, it touches your teeth first. Your teeth has a lot of calcium in it. So water and the calcium are related. Okay? So what about steam? Right? Well, the older folks might know this. A steam train. Another name for a steam train. Well, what in the old Western whatnot, cowboys and right in the 18th and the 17th, somewhere around the hundreds, the steam train, right, was called an iron horse. So that was a nickname for a steam train. So steam and the iron kind of go hand in hand. All right, so that's how I memorize it. Right, the lead and the acid. How do you know the acid is above what? It's from lead go up. Well, if you have a car battery, everybody knows what a car battery is, right? It looks something like that. This is actually called a lead acid battery. I know we just call it a car battery, but it's really the type of battery is called a lead acid. So the word acid and lead just kind of goes together. Okay? And oxygen and silver. How do you know that the oxygen, the line for oxygen is from silver go up? When you come first in a race, you get the gold medal. When you come second in the race, you get a silver medal. Silver was running the race, and he was doing real good. Silver was doing good. But then he ran out of oxygen. So when he ran out of oxygen, he lost his breath. And he came second in the race, and he got the silver medal. I don't even know if that one makes sense to you. If that doesn't make sense, just learn off the chart here. Okay? So moving on now, right? Recall how rusting works. Okay, now I haven't lost track. Remember, I need to explain how sacrificial and galvanizing works. Okay, from the last video, how does rusting work? Remember, you will have iron. Iron has 26 protons and 26 electrons. The electrons have a negative charge. For rusting to take place, the oxygen would come up to the iron, and the oxygen would basically say, "Hey, give me electrons." And when you give me the electrons, we will combine to give what? To get what? Iron oxide, better known as rust. But that's the whole point. For oxygen to combine with what? Iron, it has to give up his electrons. So the iron will lose electrons. But the question is, how willing is oxygen to give up electrons for a reaction to occur? A reaction is when two things basically combine. So iron combining with oxygen is a reaction. Now the key is, how willing is, sorry, I missed it. How willing is iron? I mean, a slight mistake, guys, please forgive me. So how willing is iron to give up electrons? Well, let's go to the list here. More reactive things are more willing to give up electrons. So the more reactive you are, the more willing you are to give up electrons. So potassium, well, most reactive means more willing to give up electrons, right? So as you go upwards, everybody is more willing to give up electrons. But look where iron is. Iron is somewhere here. Iron is kind of like in the middle, the lower middle, right? So how willing is he to give up electrons? He kind of in between. Like, I might give it up. I'm too sure if I give it up. If you ask me hard enough, I'll give up the electrons. Kind of like that kind of personality. Okay? Here's how sacrificial protection works. You have iron or steel. Let's just take the iron to make it simpler, right? So, oxygen comes up now. So this is oxygen. And oxygen is ready to create rust. He is ready to, he basically comes up and says, "Hey, iron, give me your electrons. And as soon as you give me those electrons, we will combine and make rust." However, next to the iron here, remember we connected the iron to what? A more reactive metal. Who is more reactive than iron? That's plenty to choose from. It has zinc. Well, carbon is not a metal. It has zinc, it has aluminum, it has magnesium. Let's say we choose magnesium. So now let's repeat the procedure. Oxygen comes up. If magnesium wasn't here, the iron would have given up his electrons, and the oxygen and the iron would have bonded to get rust. But he comes to this new situation now. He comes up, "Give me your electrons." But they have two people to choose from. Who will give up the electrons? As you go upwards, the metals are more willing to give up their electrons. Magnesium is above iron. He is more willing to give up the electrons. So instead of iron giving up the electrons, the magnesium gives up his electrons. And because the magnesium is the one giving up the electrons, the oxygen will be like, "Okay, magnesium, you win, I will combine with you." And instead of iron oxide forming, you get magnesium oxide. So the magnesium rust instead, and the iron is spared. So this is called sacrificial protection, because the magnesium gave his life up. He was rusted instead. But for this to work, whatever you choose as the sacrificial material or the sacrificial metal it has to be more reactive than the other metal. So you rush him now. So you rush and say, hey, you hold on, you don't give no electrons. I given up my electrons today. All right? And the same thing with iron and zinc now. Look where iron is and look where zinc is. Zinc is above the iron. So when the water and the oxygen, well, when the oxygen comes here, right, and it's time for rusting to occur, the oxygen will ask, hey, who is giving me the electrons today to turn to be rustified, right? So zinc will rush the iron and say, hey, zinc will say, iron, you hold off. I'm more reactive than you. I'm giving up the electrons. So the zinc will give up the electrons instead. And the zinc is the one who will rust, okay? Not the iron, okay? So galvanizing is a kind of sacrificial protection, except the galvanizing has two ways to protect. First of all, we made a full layer around it to prevent the water and oxygen from even touching it. But the sacrificial rusting kicks in if the zinc gets damaged. You still have a backup protection. All right? So I hope that made sense. Let's answer some quick questions I saw in some past papers regarding this here, right? If X, now we don't know what X is. X is just some metal. We don't know what metal it represents here. If X does not react with hydrochloric acid, well, some of y'all may not know what this is, but this is a type of acid, hydrochloric acid. If X does not react with hydrochloric acid, what could it be? Well, everything above this line reacts with an acid. So if X does not react with an acid, it could either be, well, hydrogen is not a metal, okay? It's just in here for what? Don't worry what it's there for, but every reactivity series you'll see hydrogen and carbon. So if it does not react with acid, it has to be below this line. So the answer in the exam will be either copper, silver, or gold. If they ask you to state one material, only one, you can choose any one of these three. If they ask you to list all three, list all three. Like what could X be? Let's try a slightly harder question. If Y reacts with acid but does not, but my English is so horrible. All right, but does not with water, what could it be? So apparently this mysterious metal reacts with acid. So if it reacts with acid, it has to be somebody above this line here, right? So it has to be somebody from here go up. But it does not react with water. So if for the metal to react with water, it has to be either calcium, sodium, or what? Potassium. So that means the answer for that one has to be lead, either lead, tin, iron, zinc, aluminum, or magnesium. All of these that I just said react with acid, but they are not reactive enough to react with water. So Y could be this, or this. You have plenty choices to put in the exam. And the last one, which is better for a cooking pot, iron or copper? So let's say I have a pot and you want to buy one, and the person at the store is selling iron or copper. Which would you choose? I would go with copper. Because iron, right, look at this. Iron reacts with acids. You know what? Everybody above this line will react with the acid. Some foods are very acidic. When you're cooking, foods have acids in them. So you don't want your iron pot reacting with the acids. You'll damage the pot over time because a reaction is occurring every time you cook. Copper does not react with acids. It's below this here. Now, it does react, copper does react with oxygen, but so does iron. So which would you prefer? something that only reacts with oxygen, or do we want a pot reacting with acids and oxygen? Copper is the better choice. The copper pot will last longer. Okay? All right? So that is that's my interpretation of how to, of which one to choose. All right? All right, so I guess it's a matter of choice. I think there's some downsides to using copper. If I missed anything, if I got anything about this particular question wrong, please put it in the comments below, right? I do make mistakes sometimes, so I'm hoping you all will, up the discussion to try to rectify any mistakes I make as part of teaching. All right, so we have to come on this board now, right? So I hope you're making notes, guys. Let's see if I can move the camera across without any problems. Feel free to fast forward at any point in time. All right. I know this could be annoying. All right. Move my camera. I think I have everything there. I believe I got everything to fit. I'm just gonna move this back a little bit. All right, think I got everything to fit. Just double checking the screen here. All right, looks like I got it to fit. Got lucky today. All right, let's see. This question, I've seen it in a past paper. Why is aluminum better for making windows than iron? So let's consider the two materials here. We have iron and we have aluminum. Well, we know once we have oxygen and water, let's make sure I put the water here, right? Oxygen and water, when it comes in contact with the iron, we know rusting will occur. So the rusting will go around the iron like this. So I draw it in orange here. Well, rust is really kind of brown orange, or brown red, however you want to describe it, right? Now the thing about it, this rust is iron what? Fe2O3, iron oxide. It's bad enough that what? The iron is beginning to rust. But here's the bad thing. The rust doesn't even form a neat layer over the iron. I'm sure you've seen rust on something. It is be flaky, and it's not like a nice smooth paint job over the iron, which is bad because it would have been super nice. Well, I think the better way to explain this is probably to explain the aluminum here first, and I'll come back to this. When the oxygen and the water come in contact with the aluminum, right? The aluminum, we can't say rusted. Remember, I tell you, the word rusted is reserved for iron. The aluminum will begin to corrode, and instead of getting iron oxide, you will get Al2O3, aluminum oxide. But here's the nice thing. The aluminum oxide layer just form a real neat layer around it, a kind of seal around the aluminum. So once that seal form, right, it's a real strong seal, right, a good seal. The Al2O3 prevents any further corrosion. That's the nice thing. So it comes like the aluminum. What was trying to corrode it now becomes its protector, and no more oxygen and water can get into contact once the initial corrosion takes place. Okay? And there's only a little bit of corrosion takes place. After that, basically for a very long period of time, no more corrosion takes place. But iron, because it doesn't form a neat layer, it leaves places exposed. And so when Fe2O3 or rust forms, over time, here will begin to rust. And the rust just completely so completely takes over the iron, it never forms a protective layer. So this is why the aluminum is lasts longer than iron. When you hear people buying windows, they just be like, all right, there's always a lot of people who build houses is be like, all right, what kind of windows are gonna buy? Iron or aluminum? The iron will be cheaper, the aluminum will be more expensive, but the aluminum will last way longer because of the nice seal formed by corrosion, and that corroded aluminum is called Al2O3 or aluminum oxide. All right, so I hope that this actually came in our past paper. Another thing that I'd like to discuss is metal alloys. An alloy is when you take two different metals and combine them together. And it changes the metal. Sometimes it makes it more dense, sometimes it makes it harder. You know, usually alloys creates an improvement. So sometimes in the exam they will ask you, what is brass made up of? To make brass, you need to take copper and zinc and mix it. If they ask you how to make steel, well, I already covered this in the last video, but just repeating it here. You just take iron and mix it with carbon, and then you get steel. Steel is actually stronger than iron. Solder, I don't know what you all know what solder is, but is use solder to like, if you have two broken wires, you can like basically weld the two wires together. If you don't know what solder is, that's okay. Just remember the word. Tin and lead is what you combine in order to make what? Solder. All these are alloys, and these are the metals used to make the alloys. Learn them off for the exam, guys. Learn them off. Okay? Then they like to ask you, very popular in the exam, like what's the main difference between metals and non-metals? Well, everybody knows a lot of examples of metals, like it have iron, it have steel, it have aluminum, magnesium, and then it have plenty non-metals. It have oxygen, hydrogen, carbon, silicon. There's so much non-metals in the periodic table also. So metals are usually shiny. Non-metals are usually dull in color. And gases, a lot of them are colorless, and some of them have color. Like nitrogen is colorless, but chlorine is a kind of greenish gas, kind of like green gas, okay? Metals are usually good conductors of heat and electricity. Non-metals are usually poor conductors of heat and electricity. Now, it has some exceptions to the rule, right? Carbon and graphite are made up of the same type of atoms. Carbon is a non-metal, but carbon is actually a very good conductor of electricity. It's one of the very few non-metals that can conduct electricity. The rest of them are just poor conductors of heat and electricity. Metals usually have a high density, except for sodium and potassium. They have low densities, but the rest of the metals, high densities. Non-metals usually have a trend. They have a low density. Metals usually have a high melting point, except for mercury, right? Mercury is the only metal that doesn't have a high melting point, okay? And non-metals usually have a low melting point. So all I can ask you to do is draw this table and learn it off. There's nothing too much for me to explain over here. All right? So guys, I think that kind of takes us to the end of rusting and metals and whatnot. In video 3, I think I'm going to handle the things like acids, bases, and salts as it relates to the integrated science syllabus. Okay, guys? And once again, guys, please share this video as much as possible, okay? And, you know, tell other people about it and whatnot. There's a lot of people who can actually use all the information here. And guys, please don't forget to read the description. There's always something important in the description. So anyway, guys, this Stay tuned for part 3 as soon as I get time. Take care, guys. Good night.